Yes. So in photochemistry, in your last class, we discussed about complete Jablonski diagram. So there are two types of loss of energies are going to be observed. That is radiative and one more is non-radiative. There we also discuss about some selective terms: vibrational cascade, internal conversion, intersystem crossing, fluorescence as well as phosphorescence. So complete explanation is given regarding Jablonski diagram. So now some selective conceptual knowledge is required regarding ISC so that we can enter into photosensitization, followed by photochemistry of carbonyl compound. So keep heading ISC. Intersystem crossing, separately we are learning intersystem crossing. See, this is thermal decay process. And this process is found to be forbidden. It is forbidden and inversion of multiplicity is observed. Inversion of multiplicity observed in case of ISC. ISC is most important for photochemical reaction, intersystem crossing. In Jablonski diagram already we discussed T1 to S1 is called inverting their multiplicity is nothing but intersystem crossing. So it is a delay process, thermally decay process, and it is a forbidden, and that is inversion of multiplicity observed in this case. So generally, if I take any carbonyl compound and benzene, then I am taking a normal diene. So here see, ISC takes place within 5 minutes, it will take place within 10 minutes, here infinity minutes it will take ISC. Intersystem crossing, it will take place within 5 minutes. So whenever if it is takes place within 5 minutes, here gap between S1 and T1 is very less. Okay, but what about here? Gap is little bit higher. Here gap is little bit higher between S1 and T1 in case of benzene. But what about in the case of diene? Diene having a highest energy gap. So this is S1 to T1. Now intersystem crossing takes place very fastly, and here it is little bit slow. Now intersystem crossing is not exist in case of diene. So intersystem conversion singlet to triplet possible only depends upon this particular gap. If gap is regularly increases, intersystem crossing is not exist. So smaller the gap, greater the overlap between singlet and triplet, and greater the ISC. And larger the gap, there is no overlap between singlet and triplet, and it is a inefficient ISC. So this is called efficient ISC, and this is called inefficient ISC, and this is called moderate efficient ISC. So as time decreases means we can convert very easily. Singlet to triplet we can convert easily, but time increases means it is not easy to convert. It is impossible to convert singlet to triplet because gap is very high. There is no overlap between singlet and triplet. If there is no overlap, it is impossible to convert singlet to triplet. Infinity minutes means we are waiting for maximum time, but still singlet is never converting to triplet, which means gap is very high. So always intersystem conversion of any molecule depends upon which one? It is depends upon gap between singlet and triplet. Smaller the gap, greater the efficiency. Larger the gap, poor becomes efficiency. Okay, so always ISC of a molecule depends upon the energy gap. This is called energy gap. I will write every time E gap. E gap nothing but energy gap between singlet and triplet. Here E gap is very high, but here E gap is less, and here it is further very less. So as E gap is regularly increases, what happens? Efficiency decreases. So for selective molecules, it is an inefficient molecule. I can say it is inefficient ISC. This is moderately efficient ISC, and this is efficient ISC. So between carbonyl compound, benzene and olefins, normal olefin and even diene also, out of these three, carbonyl compounds are efficient ISC systems. Clear? Right. So every time I will use the word E gap. E gap nothing but energy gap between singlet and triplet. So it is a thermal decay process, forbidden process, inversion of multiplicity is observed, most commonly in ISC. So now carbonyl compound will take 5 minutes for ISC. It will take 5 minutes for ISC. Within 5 minutes it converts singlet to triplet. But what about here? It will take 10 minutes to convert. It is taking infinity minute. Infinity minute means we don't know how much time it will take. And we don't know still whether it exists or not. That is called infinity minute. This is carbonyl compound like this. See, ISC of a molecule depends on, where it is depends? ISC of molecule depends on E gap, energy gap between singlet and triplet. ISC of a molecule depends upon E gap between singlet and triplet. Okay, so in efficient ISC molecule, E gap is very less and good overlap between singlet and triplet. Singlet triplet having a good overlap. That's why E gap is very less, so we can convert very fastly S1 to T1. So I can say best example, carbonyl compound. Carbonyl compounds are efficient ISC. Efficient ISC system or efficient ISC molecules. Most of the carbonyl compounds are easily convert singlet to triplet. Carbonyl compounds are efficient ISC molecule. So in that one, see, direct irradiation produce singlet. What about next one? Followed by triplet. So if I take any carbonyl compound, first if you irradiate directly, that carbonyl compound initially gives singlet, very fast it will give triplet. Which means if I take a carbonyl compound like this is S0, this is S1 and this is T1. First it will exit from here to here, singlet. Then later on very fastly it will convert into T1. Why it is converting into T1, carbonyl compound, very fastly? Because small energy gap between singlet and triplet. If this gap is very small, very fastly we can convert singlet to triplet. That is the specialty of efficient ISC. I will use only two words. Efficient ISC, inefficient ISC, moderate efficient ISC. So mostly we can forget about moderate. We want only two. Efficient ISC, inefficient ISC. Carbonyl compounds are one of the excellent examples for efficient ISC. That's why in your textbooks they will explain photochemistry of carbonyl compounds only. Due to this reason. Because singlet reactions are different, triplet reactions are different. Singlet one kind of reactions are observed. And if you want to know about triplet reactions, we need to create the triplet state. So triplet state is created by carbonyl compounds only. Due to small energy gap. When gap is very small, between singlet and triplet, overlap is very high. When overlap is very high, easily we can transfer the energy from singlet to triplet by changing their multiplicity. So ISC possible only when if energy gap is very small. This is for carbonyl compound. You can take any aromatic or aliphatic, you can take any one. So carbonyl compounds are one of the examples for efficient ISC. See, moderate ISC molecule, E gap is moderate ISC molecules having average E gap between S1 and T1. Okay, so here example for average ISC. What is an example? Aromatic hydrocarbons. Aromatic hydrocarbons are moderate ISC. You need to remember this point. Moderate ISC molecules. Efficient ISC. Efficient ISC molecules are examples. Carbonyl compound. Moderate ISC molecules are aromatic hydrocarbons. Naphthalene, anthracene, benzene, etc. So, in this case, direct irradiation very slowly generates T1. T1 generates very slowly. Possible, but it will take some time. That is called moderate. T1 possible or not? Possible, but we need to spend some time. So why it is possible? Due to average gap. So moderate overlap is observed. So this is S0, S1 and this is T1 is there. Now T1 gap is little bit high as compared to this one. So it is a time taking process. ISC is a time taking process in case of aromatic. But ISC is a very fast process in case of carbonyl compound. That's why benzene also having more number of aromatic reactions. See, divar-benzene, benzoylene, okay. So prismane, that all can be prepared by using triplet state only. But direct excitation, that will give benzene, normal excited benzene. So that's why if you get any cyclation reaction benzene, if it is observed, that is belongs to T1 state. But when if it is excited from year to year it will take very slow process. Possible, sometimes it is not even possible. That depends upon gap. But most of the aromatic compounds, forget about substitutions, maximum they can have a tendency to give T1, but very slowly. They are called moderate ISC. Clear? Is it possible to give T1 in this one? Yes. In this possible T1 in this one? Yes. Between these two, which is easily give T1? Carbonyl. So that's why first we are going to learn many photochemical reactions for carbonyl compounds only. Because our target is T1. T1 giving a different product. And that product percentage is completely higher as compared to singlet product. Because it is more stable. But getting T1 is an important factor. This T1 formation takes place depends on this gap. So this gap is very less for carbonyl compound. Only that photochemistry reactions we are going to learn. So whichever molecules having a small energy gap between S1 and T1 and whichever is giving a most eminent products at T1 state, only that particular photochemical reactions we are going to discuss. Clear? You need to know why we are learning photochemistry. That is a key advantage. So here you write one point. Next, inefficient ISC molecule, it is only one word. Inefficient ISC molecules, E gap is very high. E gap is very high. Producing absence of T1 to S1 to T1 conversion. So S1 to T1 conversion is absent. So in inefficient ISC molecule, E gap is very high. There is no overlap between singlet and triplet. No overlap. And finally, can you give an example? Example in this one is alkanes. Alkanes and conjugate alkanes. Conjugate diene or inefficient ISC. Inefficient ISC molecules. These all are inefficient ISC molecules. Alkene and conjugate alkanes or conjugate dienes are inefficient ISC. So direct irradiation produce singlet, but not possible to generate T1 state. Is it possible to generate T1 state here? No. impossible to generate T1 state because large energy gap. Moderate efficient is benzene, inefficient is simple alkene and conjugate alkene. So simple alkene and conjugate alkenes are inefficient ISC. Means it is impossible to generate T1 state. T1 state is not possible to generate in this case. So you can write like this. This is S0 and this is S1 and your T1 gap is very high. Now interconversion from here to here it is impossible. E gap is very high, not possible to generate T1 state. So in moderate possible to generate T1? Yes. In inefficient possible to generate T1? No. Even if you wait for 1 hour, 2 hour, 3 hour, singlet molecule or singlet excited state of excited partner never give T1 state due to large energy gap. But once if it is generate T1 state, suppose if it is generate T1 state, will you get different products or not? Yes. But now our target is T1, to generate T1. How to generate T1 state for inefficient molecules? That is the concept. Right or not? See, if any molecule generate T1 directly, no problem. Moderately generating, no problem. Suppose it is impossible to generate T1 state means it is an important factor because if it is generating T1, T1 products are known. If it is generating very slowly, T1 products are known. If it is not generating T1 state means, do you know T1 products? No. We need to generate T1 in an indirect way for this molecule. And we need to confirm what are the products expected at T1 state. This is ultimate target. Our target is to generate T1 state for inefficient molecules. This state should be generated by externally. That is called photosensitization. From here onward, concept is going to be changed. Photosensitization only for inefficient molecules. If you are using the word, anywhere if I use the word photosensitization, think about this molecule, inefficient molecule. Because photosensitization is a process which is responsible to generate triplet state for inefficient molecules. Normal it is possible? No. Ground state to singlet possible, singlet to ground state possible, singlet to triplet not possible, especially in this case. But triplet is giving a different products. I want to prepare that products only for this molecule. Is it possible directly? No. Indirectly possible. Indirectly I can generate a triplet state for this kind of molecule with the help of a sensitizer. That is called photosensitizer. That process is called photosensitization. Photosensitization is a process applicable for the molecules having inefficient ISC systems. Whichever molecules are unable to generate T1, for that molecule we are using a sensitizer. That is called photosensitization. Clear? Right. Clear? Now see one example. So here I am taking a benzophenone. This is called benzophenone. Now ES1 is equal to 75 kilocalorie per mole and ET1 is 69 kilocalorie per mole. These are the two energy levels of which one? Benzophenone. So what is the energy difference between S1 and T1? 6 kilocalorie per mole. Small energy gap. So I can say that energy of singlet is little bit higher, energy of triplet is, it is lower. This is S1 T1. Now ISC possible? Yes, ISC is possible. E gap is how much? E gap is 6 kilocalorie per mole. So now it is a efficient ISC. I can say carbonyl compound is efficient ISC because easily converts into triplet state, small energy gap. Now I am taking one more example for a diene. These values you need to remember for these two molecules. This is diene. ES1 is equal to 124.2 kilocalorie per mole. ET1 60 kilocalorie per mole. Okay, and if you observe clearly, energy gap is very high or not? E1 to S1. See, this is S1 and here I am writing T1. This is T1. Now I want to convert from here to here. This is called intersystem crossing. And what about E gap here? E gap value is 64.2 kilocalorie per mole. Is it E gap is very high? So I can say that singlet to triplet having a large energy gap. Remove from here to here. That is called E gap. ES1 is this, ET1 is this. So gap between this and this is 64 kilocalorie per mole. Gap is very high, that's why impossible to convert T1 state. This is called inefficient ISC. See, direct irradiation, can you get singlet? Can you get directly triplet? Possible. But direct irradiation, can you get S1? Yes. S1 possible, direct irradiation. But T1 possible? No. So which means if I take benzophenone is at ground state, S0. Photochemically irradiated. This is called direct process. Directly I can get singlet state. This is singlet state of this one. This is singlet, otherwise S1. Now further I am going to write ISC, intersystem crossing. Possible? I can write intersystem crossing. Now it is triplet state. Now I can say T1 state. Possible? What I am saying is, when you take ground state benzophenone, is it possible to generate triplet directly? No, directly it is impossible. Any molecule, directly we can't generate S0 to T1. This point already explained. See, in your examination, if they mention direct means S0 to S1, S1 to T1, that is the meaning. This is not direct. Directly we can't generate S0 to T1. Even for efficient molecule, we can't generate. First they need to reach up to S1. From S1 to T1 gap is very small, that's why it is converting into T1. So meaning of direct indicates S0 to S1, S1 to T1 very fastly. That is the meaning of direct. So don't think that direct means not this one. S0 to T1 never takes place in any molecule. Even in efficient molecule, S0 to T1 is impossible. Okay. Now see your next molecule. I am taking a diene. It is at S0. Photochemical direct I am using. Direct. What happens? Will you get any singlet state? Yes, S1 is possible. Now, this singlet state responsible to give. Suppose if any triplet is possible. Is it possible to generate this triplet? ISC possible for this or not? ISC. For diene I am saying. Gap is very high or not? S1 to T1 gap is very high. So, ISC is impossible. Suppose if any diene is given direct, if they mention, you stop up to S1. Don't write T1. Direct meaning. If I say direct, what you will write? For any aromatic, carbonyl compound, if I write the word direct, write down T1. The T1 is generated from S1. S0 to S1, S1 to T1. That is the meaning of direct. Okay. So what is the meaning of direct for inefficient system? Direct means singlet to singlet only. From there onwards it is impossible to convert T1. So is it a direct process possible? No, it is also impossible. In this it is not possible means it is not possible. Any molecule, remember, it may be efficient molecule or inefficient molecule. S0 to T1 generation is impossible directly. S0 to T1 not possible to generate because spin is inverting, not possible. Spin retention is allowed, spin inversion is Forbidden. This yesterday I explained. Allowed in forbidden transition. So if I say for this molecule, any inefficient molecule, if I use the word direct, on the time write down S1 only for this molecule. For this molecule, if I write direct, write down T1 for efficient molecules. So but T1 is generated proceeding with S1 followed by T1. It is not possible to generate directly like this. Right. This is benzophenone and this is 1,3 butadiene. Clear? So keep heading photosensitization. 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 Now ISC is over. Now three things we learn in ISC: efficient, moderate and inefficient. Now there is no problem with efficient and inefficient. Problem only with complete inefficient. Moderate efficient also there is no problem. So now we are learning especially for this case, because this case there is no possibility of generating T1. Right. See, it is an indirect method to generate T1 state for inefficient ISC molecules. It is an indirect method to generate T1 state for inefficient molecules. Try to understand the statement. Whenever if I use the word photosensitizer, sensitizer means which will activate. Photosensitization is a process. It is an indirect method to generate what we need to generate. T1 state. For which molecule I want to generate T1 state? whichever molecule unable to give T1 directly. See, is it possible to give T1? No. For this molecule I want to generate T1. Only for that molecule photosensitization concept is applicable. Only for these molecules. How to generate T1 state for inefficient ISC molecules? Only for that particular concept we are applying photosensitization. Okay, right. See, it is important photochemical process. It is important photochemical process. Now, especially in this process, triplet energy is transferred. Triplet energy is transferred. Triplet energy transferred in photosensitization. Most important in photochemical reactions is photosensitization, especially in this case, triplet energy is transferred. Right. In photosensitization, mixture of products, I am taking mixture of reactants, you write. Mixture of reactants. What are the two mixture of reactants? So here I am using two, good ISC plus poor ISC. Now two molecules I am mixing. What is good ISC? Easily create T1. What is poor ISC? Unable to create T1. So in photosensitization, mixture of reactant is irradiated with suitable lambda. Suitable lambda of good ISC. Good ISC also called efficient ISC or not? Efficient ISC. Now try to understand. Be careful, each and every point is most important. Try to understand this one. It is indirect method, important for photochemical reactions. We can transfer energy from triplet state. Now how to do this photosensitization? Especially in this one, mixture of two products I am taking. What are the mixture of two? In this reactants, mixture of reactants, good ISC, poor ISC, both are present, both are mixed together. So I am taking a lambda, that mixture is irradiated by a suitable light wavelength. That wavelength is suitable for good ISC. Means whichever lambda I am selecting, or whichever frequency or whichever wavelength of light I am selecting, that wavelength is suitable only for good ISC, because poor ISC unable to generate T1 state. So that's why no need to select a lambda which is suitable for T1. T1 of which one? Inefficient. Now how many molecules I am taking now? See, this is A and B, it is a mixture. Okay, now it is a good and this is poor ISC. Now I am selecting a lambda, this lambda suitable for good ISC only, because poor ISC unable to generate T1 state. That's why select a frequency, select a wavelength of corresponding light whose wavelength is matches to efficient ISC. Now when efficient ISC takes this lambda, then automatically it start excited and gives S1. Later on converts into T1. Right or not? And whichever reactant is going to absorb the radiation, that is said to be donor. Now see, I am selecting a lambda. This lambda is selected based on efficient ISC, right? Which is efficient ISC now? A is efficient ISC. So whichever molecule out of two is going to absorb the radiation, that particular molecule is said to be a donor. Whichever is not accepting, that becomes a acceptor. Now you need to remember which is a donor and which is a acceptor. Always remember, efficient ISC is a donor. Inefficient ISC is a acceptor. Clear? Right. So this lambda is suitable for which one? What is a here? Good ISC. Good ISC molecule or system having efficient ISC. A is a good ISC. See. Direct irradiation, good ISC molecule, intersystem molecule, generates produce S1 followed by generation of T1. So it is responsible to give event T1. Direct irradiation, good ISC molecule produce S1 followed by generation of T1. Is it right or not? Direct irradiation out of these two molecules, whichever is absorbing this wavelength, that will first generate what? S1. Then followed by generating of T1. Why they are generating? Why it is generating T1? Because due to small gap. Right or not? So, in reaction mixture, whichever reactant absorbs wavelength, that is said to be donor. Okay? That is said to be donor. So, efficient ISC molecule always acts as donor. It is always acts as a donor. Here you remember, it is a donor. Efficient ISC molecule always acts as a donor. In photosensitization, mixture of reactants is irradiated with suitable lambda of good ISC or efficient ISC. So that will generate singlet state followed by generation of triplet state. So this molecule is said to be a donor. Okay. So excited state efficient ISC. Excited state efficient ISC molecule collides with ground state inefficient ISC molecule. Ground state inefficient ISC molecule. Excited state efficient ISC molecule collides with ground state inefficient ISC molecule. Okay. So, and what happens? See, and transfers energy from triplet to ground state. And transfer energy from triplet to ground state. So this is triplet of ISC, efficient ISC, ground state of which one? Inefficient ISC. Okay. During this process, inefficient ISC Inefficient ISC directly generates T1 state. Directly generate T1 state without generating S1 state. S1 state is not possible to generate. It will generate directly T1 state. See, this point for which one? Efficient ISC. This S0 for which one? Inefficient ISC. Try to understand these 2 points. When any efficient ISC excited to T1 state, that is going to collide with a ground state inefficient ISC. Excited ISC, ground state ISC, both are collide together. Already it is at which place? T1 state. It is at which place? S0. We are not using any lambda for B. So directly this T1 of efficient ISC collide with a S0 of inefficient ISC. So it is a poor ISC. This is for belongs to which one? Efficient ISC, poor ISC. It is efficient ISC. And what about this one? Poor ISC. Now this energy transfer to this one. Right? T1 of which one? Excited state efficient ISC molecule means it starts from S0, rises to S1, then later on convert to T1. Now molecule is ready. So that is called excited ISC molecule. That is going to collide with a ground state molecule. Which is at ground state? Inefficient. That is S0. Now during this particular collision, excited efficient ISC, T1 energy is going to be transferred to S0. And whenever if that energy transferred, directly this inefficient molecule directly gives T1 state without generating S1 of its own. But normally T1 possible? T1 possible without generating S1? No. But in photosensitization possible by taking a reference. We are generating T1 of B with the help of A-T1. B-T1 is possible only by using A-T1. So during this process, inefficient ISC directly generates, inefficient ISC molecule directly generates T1 state without generating S1 state. Inefficient ISC molecule is known as acceptor. This is known as acceptor. During this process, inefficient ISC directly generates T1 state without generating S1 state. Now, inefficient ISC molecule is said to be what? Acceptor. Okay? So, if any inefficient molecule collides with the efficient molecule, and if they transfer energy from efficient to inefficient, that is called photosensitization. This process is called photosensitization. So, indirectly see, this is a donor. I am saying this is donor. So what is donor here? Is it efficient ISC or not? Efficient ISC is a donor. Now what is present? S0, S1. And here very small gap is present, that is called T1. So this is efficient. Now I am taking second partner. Who is second partner? Acceptor. So here S0, S1. This is called acceptor. This is inefficient. This is inefficient ISC molecule. Now, here see gap is very large. Here T1. T1 S1 gap is very high. This is second molecule, this is first molecule. Okay? This is donor. Now these two I am mixing initially. This T1 belongs to which one? This T1 belongs to efficient ISC. This T1 belongs to which one? Inefficient ISC. Now first what happens? See, these two I am mixing. Then I am using a lambda which is suitable for this one. First what happens, it will excite it to S0 to S1. Then it will undergo ISC. ISC possible. It is going to generate T1. Now, is it at ground state or not? Then what happens, see, this molecule collide with this one. After reaching T1 state of donor, donor collide with this one. When donor collide with ground state ISC, so now this is a collision. There is a collision establishes between them. So then what happens, see, these collisions are responsible to generate directly S0 to T1. Okay, so you can write directly like this. This is a collision between these two. This is collision partner between these two. There is a collision between efficient ISC and inefficient ISC. Efficient ISC triplet energy transfer to ground state energy level of inefficient ISC, that will take that energy directly lifted to T1 without reaching S1. Now, so whenever if acceptor accepting energy from T1, T1 reaches to ground state and this will reaches to T1 state. See, I am using two things. What are they? Donor and acceptor, right? Donor acceptor. Now I am setting a lambda which is belongs to which one? Donor. Donor will take this energy. Donor goes to which state? Donor goes to singlet state. Acceptor ground state. Now donor singlet state have a tendency to convert into ISC and this donor become triplet. Right? Now triplet donor is going to collide with a acceptor. When triplet donor collide with a acceptor, triplet donor collide with a acceptor, then donor reaches to ground state and acceptor reaches to which state? Triplet state. So this process is called photosensitization. Only this process. When this is transferring energy to acceptor, acceptor directly reaches to T1, only this process is called photosensitization. Okay? First I am mixing, this is first step. Donor acceptor mixed together. Donor reaches to singlet. Donor converted to triplet. Then triplet donor collide with a ground state acceptor. Now triplet energy transferred to acceptor. Acceptor reaches to triplet state. Donor reaches to ground state. So finally who is at ground state? Donor. Who is participating now? Acceptor. Who is acceptor? Efficient ISC or inefficient ISC? Inefficient ISC. Okay. So remember, triplet sensitizer. Who is triplet sensitizer? Donor or acceptor? Whichever partner gives energy from their triplet state, they are called triplet sensitizers. Who is triplet sensitizer? Donor or acceptor? Who is donor? Efficient ISC. Efficient ISC can generate T1. That T1 energy transferred to ground state molecule. When T1 energy transferred to ground state molecule, then myself I am a triplet sensitizer. I can generate a triplet state without reaching S1 state. Now it is a donor or not? Donor generating triplet state of inefficient molecule with the help of T1 state. Now donor is a triplet sensitizer. Donor is a triplet sensitizer. Means whichever molecule is efficient ISC which can transfer their triplet energy to ground state acceptor and ground state acceptor converts into triplet state, then this is called triplet acceptor donor. This is a triplet acceptor. It is a triplet sensitizer. It is a triplet quencher. It is a quencher. It is quenching or not? What is the meaning of quenching? Itself it is getting activated by decreasing energy of other partner. Okay? So this partner already activated. This activated partner is called donor. This partner donating electron energy to ground state partner. Which energy they are transferring? Triplet energy. That's why they are called triplet donor. This energy taken by this molecule, that's why it is called triplet acceptor. So whichever is acceptor, that acceptor is also called quencher. Every acceptor is called quencher. It will take energy, absorbs energy. That is called quencher. So who is triplet quencher? Who is triplet quencher? Acceptor. Who is triplet donor? Efficient ISC. Efficient ISC is a donor. Efficient ISC is a donor. Inefficient ISC is a triplet quencher and acceptor. Two words you need to remember. Acceptor, quencher. Acceptor, quencher, both are same. Triplet sensitizer and donor. Triplet sensitizer and he was a donor. And what about this? Triplet quencher and he was a acceptor. Right? Triplet sensitizer means, what is the meaning of triplet sensitizer? What is the meaning of triplet sensitizer? This word I will write every time on arrow. T sensitizer I will write. T sensitizer means what? Triplet sensitizer. What is the meaning of triplet sensitizer? Efficient molecule transfer their triplet energy to ground state molecule. Then ground state molecule reaches to triplet. Triplet energy directly gives to this. It is reaches to triplet without reaching singlet. Be careful here. Don't write like this. That is wrong. Triplet energy transfer to triplet. That's why it is called triplet sensitizer. It is a triplet acceptor. Also called triplet quencher. Clear? Right. Efficient ISC molecule is donor, triplet sensitizer, efficient ISC molecule is donor or triplet sensitizer. So also called triplet donor. Sometimes they will give the word triplet donor. What about inefficient? Inefficient ISC molecule. Acceptor. It is acceptor, triplet quencher. It is triplet quencher. So also called triplet acceptor. Many names are there. This is called triplet acceptor. Who is photosensitizer? Who is photosensitizer? Triplet sensitizer I am writing. Who is photosensitizer? Efficient ISC. Who is singlet sensitizer? See here what I am writing? Triplet sensitizer. Now I am saying singlet sensitizer. Singlet sensitizer means singlet energy transferred to ground state acceptor and they reaches to singlet. That is called singlet donor, singlet sensitizer. If I use your triplet nothing but triplet sensitizer gives energy to acceptor then reaches to triplet. Singlet to singlet, triplet to triplet. That is the meaning. Okay, donors are two types. Donor can deliver their energy or transfer their energy from singlet state or triplet state. They can transfer from singlet or they can transfer from triplet. Suppose if they transfer from singlet, singlet sensitizer. If they transfer from triplet, triplet sensitizer. If singlet transfer, acceptor reaches to singlet. If triplet transfer, acceptor reaches to triplet. That is the meaning. Triplet sensitizer gives energy from their triplet state, acceptor reaches to triplet. Singlet sensitizer release energy from their singlet state and acceptor reaches to singlet. That is the meaning. Clear? Who is sensitizer? Who is sensitizer? Donor. Whichever person is giving energy, he was a sensitizer. If that person releases energy from singlet state, singlet sensitizer. If they releases from triplet, triplet sensitizer. Clear? So now we are writing this photochemical reaction based on efficient ISC only. Who is giving products right now? Whether acceptor giving product or donor giving product? Acceptor. Donor is not giving product. Donor transferring their energy to acceptor. Acceptor reaches to triplet state. From there onwards we are getting product. Right? Now see this. I am using benzophenone and I am also using diene. What are the states of these two? Yes not, yes not. Now I am using lambda of which one? Lambda of donor. Who is donor here? Donor is benzophenone, diene is a acceptor. Donor, acceptor, same. Donor, acceptor. Donor reaches to singlet state. Donor reaches to singlet state. See, it is at singlet state S1. And what about acceptor? Acceptor is at ground state. Same. Donor reaches to singlet, acceptor at ground state. Now, later on, donor, due to small energy gap between these two, there is a conversion of singlet to triplet or not? Singlet to triplet possible. Now singlet converted to triplet. This is T1. This is singlet. This is your second step. Donor, acceptor both are ground state. Donor reaches to singlet. Slowly donor converted to triplet. Then after reaches to triplet, what is the next step? Triplet donor. This is triplet donor. I can write 3 outside. This is T1. Then what about ground state? Who is ground state? S0, diene. Now what happens? See, this is called photosensitization. Especially this step. Last step is called photosensitization. This step here you write down photosensitization. In photosensitization process, triplet energy transferred to ground state acceptor. When triplet energy transferred, then what is the state of donor? Donor reaches to which state? S0. Then finally, what about acceptor? Acceptor directly reaches to which state? T1 state. This is our ultimate target. Here who is photosensitizer? This is photosensitizer, also called triplet sensitizer. Photosensitizer, also called triplet sensitizer. I will write every time like that. T sense, like that I will write. SEN about T. I will write like this. T dot SENT. In exam also they will write like this. They will write T dot SEN about T, which means efficient ISC. Three-step mechanism. Photosensitization is a three-step. Donor-acceptor mixture, donor singlet, donor converted to triplet, donor transfer their energy from triplet to ground state of acceptor. Finally, donor reaches to ground state, triplet reaches to acceptor. Who is unnecessarily responding? Who is unnecessarily responding? Donor. You and your friend writing exam. This is your friend and this is you. You are not prepared exam. Both are went for the examination. Both are initially ground state or not? Both are ground state. Okay? Then, whatever paper is given, that paper convenient for which one? Your friend only, because you are not prepared anything. So you are always at ground state or not? Your friend is writing exam. Start writing exam. You are not started because you are at ground state only. Your friend is start writing exam. He was reaches to 50 marks. But you are at ground state, 0. Still you are not writing, simply you are watching here and there. And your friend reaches to almost 90%. Still no response. Then finally what happens, see, you are copying from your friend. You are transferring your friend total energy. Finally, examiner caught your friend got 0, you got full marks. Who is finally passed? Who is finally got full exam, full marks in exam? Acceptor. Those who not prepared examination, they got full marks. And whichever person is prepared very well, who is responding very fast in exam, he was responding very fastly or not? Donor responding very actively, very fastly they are writing. Finally, he was failed. 0. Initially 0. Initially 0. Before starting exam 0. Finally 0. But initially triplet acceptor initially 0. But finally, he know how to pass. He know only how to prepare. That's it. He don't know how to pass. So acceptor is your friend. Just imagine, acceptor is your friend. Donor is you. You are writing exam and you want to show your answer sheet to your friend. This is photosensitization. So you are showing your answer sheet. Why you are showing your answer sheet to your friend? Why you are showing? One purpose is there. What? This person never passed, so you need to get some marks for this person. So finally you need to get ground state. So this is called photosensitization, and this process, especially whichever is donating energy to acceptor, that is called photosensitizer. If it is giving energy from triplet state, triplet sensitizer. So that is end of photosensitization. So some selective words are appeared right now. Donor acceptor. What is one more? Photosensitization, photosensitizer, triplet sensitizer. These words are very, very important. So this will follows until completion of photochemistry. Especially ISC, triplet sensitizer. Efficient ISC, inefficient ISC, triplet donor, triplet acceptor, triplet sensitizer. These words are going to repeat. Try to remember these words. Clear? Now in that only same, it is photosensitization concept, but it is takes place within the molecule. Intramolecular photosensitization. Intramolecular photosensitization. So what is intramolecular? Donor acceptor are present in one molecule. One molecule carry donor and acceptor. They are called intramolecular. Single molecule having donor and acceptor. If donor acceptor are present in one molecule, that is called intramolecular photosensitization. So which means it is a donor and it is acceptor. So donor acceptor photochemically irradiated, donor reaches to singlet state. Donor reaches to singlet state, but what about acceptor? Ground state. Donor singlet state acceptor. Now due to ISC of donor, donor reaches to triplet state and here acceptor at ground state. Then intramolecular donor is going to transfer energy to this one. This is called photosensitization. This energy transfer to this. Now what happens? See, donor reaches to ground state and acceptor reaches to triplet state. It is also 3 step. First step, second step, third step. But both are present in one molecule. Okay, donor initially this, and always this light wavelength is suitable for donor only. Always whatever lambda I am using, light I am using, that is suitable for donor. Okay, so donor reaches to this singlet, then donor reaches to singlet to triplet ISC, then followed by what is this? Photosensitization. Who is photosensitizer now? Donor. So best example for this one is C. Always remember diene. So in this case it is a donor, and what about this part? This part is acceptor. This is example, same way. Now this is a one molecule where donor and acceptor both are present. Same, if I use a lambda, that lambda matches to which one? Lambda matches to carbonyl. Carbonyl turns to D1, then turns to D3, then D3 energy transferred to A. So finally who is activated? Finally who is activated? A is activated. A reaches to where? Triplet. Okay, so even so this molecules also belongs to this case. This one. So now this is a donor, it is a acceptor. Now next is limitations for photosensitization. What are the limitations are there? So when photosensitization is possible, that is called limitations. First limitation, always remember ET1 of donor, ET1 of donor always greater than ET1 of acceptor. This point you need to remember. Donor ET1 energy should be greater than acceptor ET1 energy. That is the first limitation. That is the selection of donor, selection of acceptor. Second limitation, ES1 of acceptor, ES1 of acceptor always greater than ES1 of donor. Singlet energy of acceptor always greater than singlet energy of donor. These conditions asking in exam, especially these limitations they are asking in DL or in any local entrances, DL and PL set examinations. These limitations they are asking. Sensitization questions are common in regular set examinations. Limitations are most. Next, see, always concentration of donor greater than acceptor. Always donor concentration is greater than acceptor. More concentration will be for donor because donor giving energy. So donor should be very concentrated. And this is last one. Now ES1 comma ET1 of donors always in between ES1 comma ET1 of acceptor. It is in between acceptor. ES1 ET1 of donor should be in between ES1 ET1 of acceptor, which means, see, this is ES1, this is ET1. Now here I am writing ES1 and this is ET1. This is ES1 of acceptor, ES1 and this is ET1. Okay, what about these two? These two are belongs to donor. These two are belongs to donor. And what about here? These two are belongs to acceptor. So what about energy of ET1? So diene, I am taking example of diene and here I am taking donor is a benzophenone. So what about this energy? 65 kilocalorie per mole. And this is 75 kilocalorie per mole. And here see 124.2 kilocalorie per mole. And what about this energy? 60 kilocalorie per mole. Just see in your notes. See, it is 124, 60. These two energy levels are higher and lower between these two or no? Acceptor ES1, acceptor ET1. These two are very higher and this is very lower. And whatever donor energy levels are present, ES1, ET1 energy levels, these two energy levels are in between these two only. Then only it is behaves as a donor. Try to understand. Focus on acceptor. What is acceptor ES1 energy? 124. What is acceptor